welcome back. This is really an extension of the last video on gravitation because I realised we hadn't really covered anything on orbital period or escape velocity, and there is quite often questions that cover either of both of those things in the past papers. So let's have a look at a couple of them, and we'll start off with the 2016 paper, and it's question 3. And as usual, it might be a good idea to have a go at the question first on your own and then come back and see how we have done it. So, if you've done that, here we go. Question 3. A spacecraft is orbiting a comet as shown in figure 3, and the comet's a sphere with a radius of 2.1 times 10 to the 3 metres, and it's got a mass of 9.5 times 10 to the 12 kilograms. Part A. A lander is released by a spacecraft to land on the surface of the comet, and after impact with the comet, the lander bounced back from the surface with an initial upward vertical velocity of 0.38 meters per second. And by calculating the escape velocity of the comet, show that the lander returned to the surface for a second time. Well, there's that word calculate, so let's go straight to the relationship sheet and find the relationship for escape velocity. There it's there, so let's write that down first and then see what values we need to substitute into this relationship then. So it's the square root of 2gm over r. Big G you'll find on the data sheet. That's 6.67 times 10 to the minus 11. And m is the mass of the comet, 9.5 times 10 to the 12 kilograms. And r is the radius of the comet, which again is given in the stem of the question there. It's 2.1 times 10 to the 3 metres. And if you do that on your calculator, you'll get an answer of 0.78 metres per second. So, if the initial vertical velocity of the lander was 0.38 meters per second, then that is less than the escape velocity, so the lander will return to the surface of the comet. Let's have a look at the marking instructions, which again I'm getting from the Calder-Glen High School Physics website. So, the 2016 marking instructions, question 3, and there we have the 3 marks for relationship, substitution and final answer for the escape velocity, and then the final mark for saying that the lander returns to the surface because its velocity is less than the escape velocity of the comet. 3 part B. Show that the gravitational field strength at the surface of the comet is 1.4 times 10 to the minus 4 newtons per kilogram. Well, we have to start off with relationships from the relationship sheet and explicitly show every step to get to that final answer. So we're going to start off with the gravitational force relationship, F equals gmm over r squared, and the weight relationship, W equals mg. So the weight of an object is equal to the gravitational force of attraction. Let's sub in both those relationships. So mg is equal to gmm over r squared. We can cancel out the small m's on each side there, and therefore g, the gravitational field strength, is equal to gm over r squared. Then we'll sub in the values that we know. Big G 6.67 times 10 to the minus 11, that's from the data sheet. The mass of the comet, again, that was given right at the start of the question, is 9.5 times 10 to the 12 kilograms. And the radius of the comet from the start of the question was 2.1 times 10 to the 3 metres. And don't forget to square that. And you do that in your calculator, it gives you the answer that we're looking for of 1.4 times 10 to the minus 4 newtons per kilogram. And make sure you give your answer exactly as it was given in the question. It's a show question. Let's have a look at the MIs. So 1 mark for both equations, 1 for equating them, and 1 for the substitution. Nothing for the final answer, but it has to be there. In fact, if we look at the right hand side of the marking instructions, it says if the final line is missing, then you can only get a maximum of 2 marks. If the second line was missing, then you're only getting 1 mark for the statement that the gravitational force is equal to the weight. And here's the sore one. If you start off with G equals gm over r squared, you're going to get 0, because that isn't on the relationship sheet. You've got to start with relationships from the relationship sheet. Okay, part 2. Using data from the space mission, the student tries to calculate the maximum height reached by the lander after its first bounce. And there's the students working. And they have used their value of 1.4 times 10 to the minus 4 for the acceleration in that relationship. And they've correctly said that it should be a negative acceleration because the lander's going to decelerate upwards. Now, the actual maximum height reached by the lander was not as calculated by the student, and we've to state whether the actual maximum height reached would be greater or smaller than calculated by the student, and you've got to justify your answer. Well, the key point here is that G is not constant. The gravitational field strength will decrease with height. If we look at that relationship, as R increases, G decreases and G and M are constant. So the height reached by the lander will be greater, because if the acceleration is decreasing, then S in that relationship will be increasing. That's pretty tricky. Let's have a look at the marking instructions. It's 3 marks, so 1 mark for saying the height will be greater because A is decreasing with height. That's pretty tricky. Anyway, let's have a look at another year, another paper, another question. This is 2018, and we're going to have a look at question 4. So this is question 4. Again, if you want to do the question first, come back once you've had a go at it. Astronomers have discovered another solar system in our galaxy, and the main sequence star, HD 69830, lies at the centre of the solar system. They always give these stars crazy names. Anyway, the solar system also includes 3 exoplanets, B, C and D, and an asteroid belt. And the orbit of exoplanet D can be considered circular, so that's the one we're interested in. And to a reasonable approximation, the centripetal force on exoplanet D is provided by the gravitational attraction of star HD 69830. That's another show question, and we have to show that for a circular orbit of radius r, the period t of the planet about a parent star of mass m is given by the relationship t squared equals 4 pi squared over gm times r cubed. Now, you may have seen that relationship before. You might even have heard of it being referred to as Kepler's third law, but it is not on the relationship sheet. But this monster's on the relationship sheet. In fact, it's only a recent addition, and it's equating the gravitational force with the various forms of the centripetal force relationship. And that's all we really need here, but that wasn't added to the relationship sheet until 2019. So back in 2018, you had to do this the long way. So you had to start by saying that the centripetal force is provided by the gravitational force. So gmm over r squared is going to be equal to mr omega squared is the easiest way to do this. Now, omega equals 2 pi over t is also on your relationship sheet, and if we square all that, we get omega squared equals 4 pi squared over t squared. And then it's just a case of subbing in for omega squared on the left hand side there. So gmm over r squared will be equal to mr times 4 pi squared over t squared. And then we just want to rearrange that with t squared on the left. So let's cancel out the small m's. So t squared will be equal to 4 pi squared over gm. And then we can combine the r's here, take the r squared up, and that becomes r cubed. And that's the relationship we were required to show. Let's have a look at the MIs. Remember, these MIs are based on an older version of the relationship sheet. So 1 mark for equating centripetal force and gravitational force, 1 mark for showing those two relationships, and 1 mark for substituting in that omega equals 2 pi over t. and then rearranging for t squared. But bear in mind that this is now on your relationship sheet. This is the newest version, and all that work has kind of been done for you. Anyway, let's move on. 4a part 2. Some information about the solar system is shown in the table below. Remember, the one we're interested in is exoplanet D, which is in its circular orbit. And we've to determine the mass in kilograms of the star, HD 69830. Well, this is part 2 of the question, so it's linked with part 1 of the question. And so we're going to have to use the relationship that we were asked to show in part 1. So let's write that down again. T squared equals 4 pi squared over gm times r cubed, and it's m we're looking for. And we can use all the data for exoplanet D. So we've got the orbital period, that's t, although it's in Earth days, and we've got the radius, but it's in astronomical units. So what we have to do is we have to work out what the period will be in seconds and the radius will be in meters. So let's do the period first. It's 197 Earth days. So if we want to convert that into seconds, it'll be 197 times 24 hours times 60 minutes times 60 seconds. And don't forget to square it. And that will be equal to 4 pi squared over g, which is 6.67 times 10 to the minus 11, times the mass of the star, which is what we're looking for, times the radius. Now the radius is 0.63, but that's astronomical units. And we can find out what an astronomical unit is on the data sheet. So let's scroll all the way back to that. And there it is. 1 AU, 1 astronomical unit, is 1.5 times 10 to the 11 meters. So to convert astronomical units into meters, you multiply by 1.5 times 10 to the 11. And don't forget to cube that, because it's r cubed in the relationship. And now we have a mammoth rearranging to do to work out m. So let's move things around. Let's get m on the left hand side. So m will be equal to 4 pi squared times 0.63 times 1.5 times 10 to the 11. Remember, that's cubed. All divided by 6.67 times 10 to the minus 11 times everything that was on the left hand side there. And then if you do that on your calculator, you'll get an answer of 1.7 times 10 to the 30 kilograms. And that's worth double checking. There's the marking instructions. It's worth 3 marks. 1 mark for the conversion from astronomical units into meters, 1 mark for all the correct subs, and 1 mark for the correct final answer. Very tricky arithmetically there. Okay, part B. 2 asteroids collide at a distance of 1.58 times 10 to the 11 meters from the centre of the star, and as a result of the collision, one of the asteroids escapes from the solar system, and we have to calculate the minimum speed that the asteroid must have after the collision in order to escape from the solar system. Well, I've highlighted the word escape twice, so it's escape velocity we're interested in. So from your relationship sheet, the escape velocity is the square root of 2gm over r. And we'll sub in for big G at 6.67 times 10 to the minus 11 times the mass that you worked out in part A. So 1.7 times 10 to the 30 divided by the radius we were given, 1.58 times 10 to the 11. And if you do that in your calculator, your escape velocity is equal to 3.8 times 10 to the 4 meters per second. There's your marking instructions. Straightforward 3 marker, equations, substitutions and final answer. And on the right hand side there, you will still get the marks as long as your mass is consistent with that you worked out in part A. So 2 very similar questions, a lot of toing and froing with the data sheet, which is the case with gravitation, and an awful lot of calculator work and chances to mess up with your arithmetic, so double check your answers. And as always, do as many past papers as you can. Best place to go if you're looking for particular key areas is Mr Davie's interactive PDF of past papers. It's a fabulous resource. Next time, we'll be looking at general relativity. See you in the next one.